We construct irreducible invariant subspaces of V tensor n, and more precisely subspaces that are invariant and irreducible under Sn. And here we claim that we can simply take some starting vector in V tensor n and then apply a left ideal to this. So recall that this L lambda, that's just the group algebra, and then we project using a Young operator. Now we can apply this to some vector in V tensor n because we have this representation of Sn and of the whole group algebra, so we can take any element here from L lambda and apply it to alpha, and this is this subspace T lambda alpha, which we want to study now. Okay, first let's show that it's invariant, this subspace. So to this end, consider some vector of T lambda alpha. Then there exists some element, let's call it R, in this left ideal L lambda, such that R times alpha is just V. So V is R applied to alpha. And now let's study what happens when we apply a permutation to this vector V. Well, then we get PR alpha. But since this is a left ideal, the R is from the left ideal, so the PR is also in this left ideal. Which means that PR alpha is also in T lambda alpha. So we immediately have invariance here. Now, what about irreducibility? We will first show property 2, and that will automatically prove irreducibility. So in 2 we claim that this T lambda alpha carries the same representation as L lambda. How can we see that? Let's say we choose a basis, basis of L lambda. Let's call the basis vectors Ri. And from this we get a basis of our T lambda alpha. We're just applying the basis vectors to alpha. So Ri alpha. That's the basis for T lambda alpha. Now what happens when we act some permutation P on an element of this basis of L lambda? We get a linear combination of the basis elements. So I use summation convention here. We sum over repeated indices, and I get Rj gamma lambda Ji. So we sum over J. And this is just the representation which this left ideal here carries. Okay. Now we can apply a permutation P to Ri alpha. That's a basis element in here. But we know what P times Ri is. It's just Rj gamma lambda of P Ji, sum over J, times alpha, and if we like, write the matrix element here to the very right. Sorry, it's a gamma lambda of P, index Ji. So So we see that we get a linear combination of the basis elements, and the coefficients are just the same as here. So this T lambda alpha really carries the same representation as L lambda, but L lambda is a minimal left ideal generated by a primitive idempotent, the Young operator. So it's a minimal left ideal, and as such it carries an irreducible representation, and this is how we show irreducibility here.